This is a presentation accompanying my essay on the Yoneda Lemma. We will be covering some very basic category theory with minimal formulae involved. Everything in this presentation is very much simplified as it is just an introduction. So with that out of the way, let's begin. Here is a formal definition of a category. Don't worry about reading it, we'll be going through it soon, bit by bit. But many structures in mathematics come alongside some notion of maps, which are used to relate different objects with those structures. For instance, groups come alongside groups homomorphisms, vector spaces with linear transformations, probability spaces with measurable function, and topological spaces with continuous maps, to name a few. A category is a collection of objects with arrows or maps between those objects called morphisms, and that's it. All of the previous examples are thus specific types of categories, and many common constructions in all of these fields do not actually rely on the specifics of that field, and can be carried out and unified together when at the level of a category. The most common of these constructions are products and coproducts, direct sums, kernels, that kind of thing. We unfortunately don't have the time to cover these things in particular detail, but it's a good motivation as to why category theory is studied. Oh, and it's also important to type theory in functional programming. We begin with objects. An object can be really anything we want, but we often work with mathematical objects, such as numbers, or sets of numbers, often with additional structure on top, like groups or fields. The collection of objects in the category C forms a class called the objects class of C. And note I said class there and not set. This is because these collections of objects don't usually count as sets under Z of C. For instance, the set of all sets would be disallowed under Z of C, but such a collection of objects is useful to use, in category theory anyway, so we use classes instead. Next, we have morphisms. For any two objects, A and B, we can have a morphism between them. It can be helpful to view a morphism as a type of directional relation. There is a morphism f from A to B if A is related to B, but B does not have to be related to A, and we write this to note this relation. We can also have multiple morphisms from A to B if A and B are related in multiple ways. But it could also be the case that A and B are not related at all. For any two objects A and B, the collection of all these morphisms forms the Hom set of A and B. In the case where A is not related to B, this Hom set is empty. And because morphisms are directional, note that the Hom set of A and B is not the same thing as the Hom set of B and A. And, again, despite the name, Hom sets do not necessarily count as sets. We'll largely be ignoring the distinction in this introduction, as the categories we construct will be locally small. This means that the class of morphism between any two pairs of objects does happen to be a set. If the object class is also small, then the category itself is called small. The collection of all Hom sets in the category C is also written like this. Of course, now that we have things that point from one object to another, we want to be able to combine them. So, if f is a morphism from A to B, and g is a morphism from B to C, then we require for there to exist a composition morphism from A to C. Compositions have to obey two axioms, the first one being the identity axiom. For any object A, the category requires an identity morphism from the object to itself that follows a few constraints with respect to the composition. Identities must compose with any other compatible morphism and leave them unchanged. They're the neutral elements of composition, just like 0 for addition or 1 for multiplication. The second axiom is associativity. It just states that composition is associative, nothing special there. So, these are the things that a category is composed of. Let's go through a few simple examples. Let the object class of C contain A, so the category only contains a single object. Categories require identities, so we have that in as well. But the identity morphism by itself trivially satisfies the identity and associativity axioms, so this category is called the trivial category. And apart from the trivial category, we usually omit the identity morphism from these diagrams. Let the object class of C contain A and B, the Hom set of A and B contain F, and the Hom set of B and A be empty. This is the arrow category, consisting of a pair of objects and a single morphism between them, pointing in one direction only. So let's move on to some more interesting examples. Let G dot be a group, and let the object class of C contain a unique object X. We set the Hom set of X to X equal to G, and define the composition of F and G to be G dot F, so morphisms have group structure under composition. Because groups require associativity and identity, the morphism axioms are satisfied, and we see that a group is really a miniature one-object category. In fact, there's nothing really specific about groups here. We could have started with a monoid or any other algebraic structure that has identities and associativity. So these last few categories are pretty simple, but they give us an idea of how basic categories can be. We visit a few more important categories now. We have set, the category of sets and set functions. Objects are, unsurprisingly, sets, and morphisms are functions between those sets. Identities are just the identity function in each set, and the identity and composition axioms follow from the basic properties of functions. We also have group, the category of groups and group homomorphisms. Homomorphisms are just functions that happen to respect group structure, so identities and associativity are inherited from set. We have top, the category of topological spaces and continuous maps. We have vector sub k, the category of vector spaces over a field k, and linear transformations. These last few examples might give the false impression that objects are always sets, perhaps with extra structure, and morphisms are functions that preserve that structure. But this doesn't have to be the case. We build another simple example of this now. The objects in our categories will be the real numbers, and we define the morphism from x to y if x is less than or equal to y. The problem here is that we can't really say what a morphism is. It's not a function that acts on anything like a function in set, and in fact it doesn't seem to do anything at all other than existing whenever x is less than or equal to y. The morphisms f and g imply that x is less than or equal to y, and y is less than or equal to z. So we have x is less than or equal to z by transitivity, so there is this morphism to assign the composition of f and g. We also have x is less than or equal to x for all real numbers x, so identities also exist. Associativity and identity axioms are also easy to verify. So the set of real numbers equipped for the non-strict ordering is a category. And again, there's nothing specific to the real numbers here, so any set equipped with a non-strict order is in fact a small category. So, given some existing categories, there are two ways to construct new categories that are of interest to us. There are more, but these are the two that I want to talk about. So, if you have categories C and D, we construct the products category by taking the Cartesian product of their object classes and by matching up compatible pairs of morphisms from the original category. This looks a little complicated written out symbolically, but basically, if you have a morphism f from a to a prime in C, and the morphism g from b to b prime in D, then in the product category C cross D, we have the morphism fg from av to a prime b prime. We just take pairs of objects and compatible morphisms between them in the original categories. Next, given the category C, we construct the opposite or dual category C-op by reversing the direction of all arrows in the category. We know that this operation is an involution, so the dual of a category is just the original category, because just reversing the arrows twice just gives you the arrows back. This leads to an interesting theorem. The principle of duality states that every categorical definition and theorem has a dual definition and theorem obtained by reversing the direction of all morphisms in the category involved. We often prefix a dual notion with co, such as products and coproducts, or domains and codomains. The proof is pretty simple. If a statement holds in the category C, then the dual statement holds in the dual category C-op. But every category is the dual of its dual, so the dual statement also holds in all categories, as required. We've already been using arrows to show morphisms between objects, but we can do a lot more with these diagrams. If we take a selection of objects in a category and draw morphisms between them, then we can compose morphisms by following a path through the diagram. Because of associativity, each path corresponds to exactly one composition morphism. This is useful enough by itself, but certain diagrams have an additional helpful property. A diagram is commutative if for every pair of objects in the diagram, all routes between them are equivalent. For example, this diagram here is commutative if and only if h is equal to the composition of f and g. Now, suppose we have objects A and B in the category, and morphisms f and g such as this diagram commutes. That is, f composed with g is the identity on A, and g composed with f is the identity on B. Then, f and g are called isomorphisms, morphisms with inverses, and we alternatively label g as f inverse. If a like morphism between A and B exists, then we write this symbol to denote this relation. An isomorphism is the mathematical way of saying that we only care about some specific property of an object. You've probably heard that a topologist cannot tell the difference between a coffee mug and a donut. This is because in top, these two objects have the same number of holes, a topological invariant that does matter in top, and they can be bicontinuously and bijectively deformed into each other, so they're isomorphic. One central theme of category theory is the idea of mapping between objects. Whenever we encounter a new type of mathematical object, we should always ask if there is a sensible notion of a map between them. But of course, categories are also mathematical objects we can ask this question on. Let C and D be categories. A functor, f, consists of two parts, a mapping on objects and a mapping on morphisms. The object mapping just maps objects x in C to an object fx in D, nothing unusual here. But the morphism mapping maps morphisms in C to corresponding morphisms in D, as in the morphism has the corresponding objects on either end, as defined by the object mapping. But this mapping is subject to two constraints. Basically, functors have to send identities to identities, and they have to preserve compositions. As a consequence of this, functors preserve the commutativity of diagrams. We're not going to cover the proof here because it is just a bit of algebra and it's chasing symbols around, but it follows quickly from the second constraint. In particular, functors preserve isomorphism diagrams, so if f is an isomorphism in C, then f of f is an isomorphism in D. This definition is rather long, so more concisely we could say that each pair of objects A and B induces a mapping that respects the structure of the categories. So functors act as morphisms between categories. They compose by composing these induced functions, and identities are just the identity functors from a category to itself. This suggests the construction of a category where objects are categories and morphisms are functors, and indeed we have cat, the category of categories. We also have little cat, the category of small categories. This is a subcategory of capital cats, but we're not going to go into that at the moment because there's way too much to cover. Now, for a small bit of terminology, the functors we've been considering so far are sometimes called covariant functors. A covariant functor from C to D is just as shown here. This is in contrast to a contravariant functor. A contravariant functor from C to D is just a functor from C up to D. So we would say that the upper functor is a covariant functor from C to D, whilst the lower functor is a contravariant functor from C to D. This is mostly just a terminology/notation thing. Like, if we're working with a named category like set, it might make more sense to say that a functor is covariant than to start writing set up everywhere. We'll give a few specific examples of functors now. A forgetful functor does nothing to the objects and morphisms in the category, apart from forgetting some additional structure that mattered in the original category. For instance, we have the forgetful functor from group to set. Every object in group is a group, that is, a set to G with some extra structure in the form of a binary operation and a set of axioms. The forgetful functor U forgets this extra structure on objects, mapping groups to their underlying sets which are just objects of the category set. Similarly, morphisms in groups are groupable morphisms, which are just set functions that happen to respect this extra structure. Forgetting that extra structure still leaves a normal set function, or a morphism in set. Forgetful functors don't have to get all the structure on the object either. Consider a ring R. Mapping R to the underlying set S yields the forgetful functor from ring to set. If we keep addition and the additive identity, we get a functor from ring to the category of abelian groups. If we forget commutativity on top, we get a functor from ring to group. Let G dot be a group, interpreted as a category C with a unique object X. We will construct a covariant functor F from C to set. We only have one object in C, so we choose a set S to map X to. Every morphism G must be mapped to a function f of G from S to S in set. However, we still need the functor axioms to be satisfied. There are two natural ways to do this. We can either define the function f of G by left multiplying by G, or right multiplying by G. It should be clear that the two functor axioms are satisfied by either definition, so this choice is rather arbitrary, but we'll pick the upper option here since it more closely matches existing notation. We can really interpret this mapping to be a two-argument function, taking a morphism from G and an element little s from S and returning their product. So, f is determined by the choice of a target set, S, and a function from G cross S to S. We can then see that a covariant functor from a group to set is really just the left action of a group on some set S, or a left G set for short. For a contravariant functor, we just pick the other mapping, so a contravariant functor is a right G set. So, as we said earlier, whenever we encounter a new type of mathematical object, we should always ask if there is a sensible notion of mapping between them. Well, functors are mathematical objects, and can we map between functors? Yes, of course we can. These maps are called natural transformations. F and G each map objects and morphisms in C to objects and morphisms in D. To define a mapping from F to G, we want to associate objects and morphisms in D mapped by F to objects and morphisms in D mapped by G. So, first, consider the effects of f and g on a single object, x, in C. X is mapped to two objects, fx and gx, in D. Since we're trying to define a map from f to g, it would seem sensible for us to associate these two objects together. But since fx and gx are just objects in the category, such a relation is just a morphism in D. So eta maps each object x to a morphism from fx to gx, called the component of eta at x. However, we should recall that there are possibly many morphisms in the Hom set of fx and gx. So which one should we pick? To help us decide, consider a morphism f from A to B in C, in the left there. The top and bottom are just the same diagrams before, they've just been skewed slightly so we can draw other morphisms in. But under f and g we have two additional morphisms, f of f and g of f. Probably should have picked different letters here, but we'll work with it. So we want to relate these two morphisms under our natural transformation, since looking for a map from f to g. We also have two morphisms we want to assign to be components, a to A and a to B. These morphisms we can control, these are the ones we're trying to pick. But on the square on the right, there are two paths from FA to GB. We can either take the upper route or the lower route. If the components are assigned arbitrarily, these paths are not necessarily equal, and there could be many such possible paths. But we can use this to relate f of f and g of f by requiring that the square commutes. This is called the naturality requirement. So, overall, a natural transformation is just a collection of morphisms in the target category indexed over objects in the source category, such that this diagram commutes. Now that we have a notion of mapping between functors, we want to compose them. So how do they compose? Consider the following setup. Here, C and D are categories, F, G, and H are functors, and alpha and beta are natural transformations. From the diagram, it would seem sensible to define the composition of alpha and beta to be a map from F to H. Such a composition of natural transformations is called a vertical composition. There's also a notion of horizontal composition, but it's not super relevant to the construction we're leading up to, so we'll leave it out. Consider an object x in C. The two components of alpha and beta are alpha x from f of x to g of x, and beta x from g of x to h of x. Because these are just ordinary morphisms in D, they can be composed according to regular morphism composition rules, so we define the component of the composition of alpha and beta at x to be this composition. We still need to show the naturality of this new composition transformation, but that's simple enough. We just glue two naturality diagrams together. Because alpha and beta are natural transformations, they individually satisfy the naturality requirement, so each square commutes individually, and hence the diagram as a whole also commutes. So this composition is natural as required. Putting the components together, we get this definition of the vertical composition. With this, it's clear that identity natural transformations leave other natural transformations unchanged under vertical composition, as one of the components will just be the identity. For any two categories, we can now define functors between them, and natural transformations between those functors that obey the morphism axioms. This suggests the construction of a new category. For two fixed categories, C and D, we construct the functor category by taking objects to be functors from C to D, morphisms to be natural transformations, composition of morphisms to be vertical composition of natural transformations, and identity morphisms to be identity natural transformations. Recall the isomorphism diagram. Here, A and B are objects while F is a morphism. If we take the case of a functor category, we have this instead. Now objects are functors and morphisms are natural transformations. In this case, we say that F and G are naturally isomorphic. Because this is just an isomorphism in a particular type of category, we reuse notation and we write this. We also say that F is isomorphic to G naturally in X whenever we need to bind a variable. Note that this is very different than these objects being isomorphic for all X. The upper statement is a statement about the functors f and g, while the lower is a statement about the objects in the target category. F of x and g of x being isomorphic naturally in x is a far stronger condition than f of x and g of x being isomorphic for all x. It could be the case that these objects are indeed isomorphic, but there doesn't exist a natural transformation from f to g at all. But natural isomorphism does imply that every pair of corresponding morphisms are isomorphic as well, so this isn't actually an implication. And in fact, if we were given a natural transformation from f to g, then this implication is biconditional. Suppose we wish to study the properties of an object A in a locally small category C. One way to do this is look at A from all of the possible objects and examine it that way. By looking at how A is seen from other objects, we can obtain a lot of information about A. But thinking about the totality of maps from every other object to A is rather hard, so let's just pick one object X and look at A from there to start with. The relationships an object X had with A are exactly the Hom set of A in X and the Hom set of X in A. Let's just consider the former for now. As we move between objects, we see A from different viewpoints. If the category is locally small, then what we're really doing is assigning a set to each object. Sets are objects in the category of set, so we've really just defined the function from the objects of C to the objects of set for a fixed A. As it turns out, every morphism x to y induces the functions from the Hom set of A and x to the Hom set of A and y. So, this is just a morphism between two sets in set, and the whole thing describes a functor from the original category to set. Let C be a locally small category, and fix an object A in C. We define the covariant Hom functor from C to set, also denoted h sub A, as follows. For each object x in C, define the Hom functor to map x to the set of maps from A to x. We can interpret this as the Hom functor mapping objects to how they are seen by A. For each morphism f from x to y in C, define the Hom functor to map f to a function Hom of A in f, defined by postcomposition by f. That is, we map each morphism G from X to Y to the composition of G with F. Or in the diagram, we comb the morphisms on the left through to Y through F. We can interpret this as the Hom functor mapping morphisms F from X to Y to how A sees the object Y through F. Use whichever visual you prefer, diagrammatic or symbolic. I initially found the diagram more enlightening, but it's become less and less useful the more I actually work with categories algebraically. The contravariant Hom functor is defined dually, mapping objects and morphisms to how they see B rather than how they are seen by B. We haven't actually proved that either one is a functor, but it is again just a bit of algebra. And you only have to prove it one because the principle of duality proves it for the other. For each object A, we've now assigned a functor, h sub A, from C to set, encapsulating how the category is seen from A. But since it's the same category being seen from all objects, it wouldn't be unusual for us to expect that this assignment has some internal consistency. As it turns out, each morphism f from A to V induces a natural transformation h sub f from h sub E to h sub A. Note the change in direction here. A collection of covariant functors come together to define a contravariant natural transformation. And if we started with the contravariant Hom functors, they would all come together to define a covariant natural transformation. We'll show how this works now. Consider the components of this natural transformation as an object x. Recall that this map just sends morphisms from B to X to a morphism A to X. We can alternatively interpret these Hom sets as contravariant Hom functors with a fixed X. But we've already seen this before, or at least the dual of it. This is given exactly by precomposition by F. And in fact, there's no reason why we should have to fix one argument at a time. The notation here suggests that we may take both inputs of the Hom functor to be variable. Let f from x to y and h from b to a be morphisms and consider this diagram. Consider a morphism g from a to x in the top left here. We'll follow how it's mapped under the square along the two different paths in a technique called diagram chasing. Along the upper path, we precompose with h before postcomposing the result with f. Along the lower path, we postcompose with f before precomposing the result with h. But by associativity of morphism composition, we see that these paths are equal and that the diagram commutes for any points of g. This suggests that the double argument Hom functor is a bifunctor from C cross C to set, covariant in the first argument and contravariant in the second. A functor, f from C to set, is representable if it is naturally isomorphic to the Hom functor for at least one choice of A in C. The object A along with the natural transformation are then a representation of f. It turns out that A is determined uniquely up to isomorphism in C. The name is also rather suggestive of the fact that A in some way determines f, which is a corollary of a lemma we'll prove later. We give a few examples of representable functors. The identity functor from set to set is represented by the singleton set 1. Any function from the singleton set to a set x just amounts to picking elements from the set x, so there are exactly as many functions 1 to x as there are elements of x, which is exactly the statement of this isomorphism. Naturality follows directly from the associativity of function composition. The forgetful functor from group to set is also representable. Actually, forgetful functors in general are representable, but we'll just look at the forgetful functor for groups for now. We're looking for a group that satisfies this condition. Take a moment to see if you can spot it. All good? The additive group of integers is what we're looking for. Let G be a group, and let phi be the group homomorphism from Z to G. Because group homomorphisms send identities to identities, 0 is always sent to the identity in G. This is also why we can't pick the singleton set to represent this functor. This requirement stops us from mapping the sole elements in the singleton set to the whole group. However, we're free to pick the image of 1 in Z, which also determines the rest of the map due to the cyclic nature of Z. This suggests that we send each homomorphism to its determining value at 1, and this mapping defines the components of the natural transformation alpha. This map is also inverted by sending each element G to a map that sends integers to that power of G. Naturality is shown by chasing f around this diagram. I'm not going to talk through this one, it's just evaluating and simplifying the functions at each step. Pause if you want to read it through and make sure you've understood what each function is. We can also represent the functor that sends a ring to a set of units. We can't pick the integers here because ring homomorphisms require us to send both identities to their corresponding identities, so 0 is sent to the additive identity and 1 is sent to the multiplicative identity, so we don't have any variables free. This just gives us a point. If we try a polynomial ring, then Z is fixed by the homomorphism requirements, and the free variable is free to pick out points in R, so we just get all of R back. To ensure we only pick elements which have inverses, we use the ring of Lorentz polynomials, which you might recognize from Lorentz series in complex analysis. We give an example of a non-representable functor next. Consider the functor from set to set to find an object by mapping each set x to the coproduct of x with itself. You might also call the coproduct of this joint union in set theory. If you're unfamiliar with it, it's just the union operation, but we keep track of which set every element came from. Now, suppose there exists a set y, such that the Hom set of y and x is isomorphic to the coproduct of x with itself. If we take the case where x is the singleton set, then the Hom set of y and x is just the singleton set. But the coproduct of the singleton set with itself is the set with two elements, so these sets are not isomorphic, and hence no y exists. One almost universal problem in mathematics is to figure out how to describe and classify objects. While a mathematical axiomatic definition of an object certainly distinguishes that object away from any others, this doesn't tell us much about the collection of all these objects as a whole. For example, while we can define a group in 4 short axioms, classifying all groups is a much harder problem. In fact, we've only done it for finite groups, and even then, it took thousands of pages, tens of thousands even. For a simpler example, imagine we're tasked with classifying the real numbers. The real number line is a classification of all real numbers by embedding them in some space that has more properties than the real numbers had alone. For instance, the number line is a smooth manifold, a metric space, a topological space, etc. While we can define real numbers with Dedekind cuts or with completeness axioms, this kind of embedding gives a lot of additional and useful information that isn't visible from the axioms alone. Importantly, there's a bijection between points on the number line and the real numbers, but we also have the new information in that the real numbers near each other on the number line are similar in magnitude. We can try to extend this idea of a classifying space to other kinds of objects, where nearby objects have more similar properties than distant objects. Unfortunately, this classifying space for any kind of useful object is often completely unrecognizable and has very few properties we can leverage to our advantage. However, we can attempt to examine these spaces by looking at the maps from other spaces to them. Let 1 be the set with one element. Any map from 1 to R effectively amounts to picking an element from R, so there is a bijection between the functors 1 to R and the points in R. And in fact, there's nothing specific about R here. More generally, the maps from the one-point space 1 to any space x amounts to picking points from x. If x is a metric or topological space, then this is a set equipped with an extra structure in the form of a metric topology. By examining the maps from 1 to x, we can recover half of that information. Just by looking at x from the simplest possible non-trivial space, we recover all of the points of that space. Now, what if we look at maps from a more complicated space? A map from the interval 0, 1 to x is just a parameterization of a curve in x, so the maps 0, 1 to x recovers the paths in x, while a map from the circle S1 to x is just a topological loop, so the maps S1 to x recover all the loops on x. The point is, we get more and more information about any space x by examining how it appears from other probing spaces. But exactly how much information can we recover? Is it always possible to obtain as much data from looking at maps as we would from just analysing the space itself? After all, we have no reason to expect that the entire structure of the space is always captured by these maps. Except, it always is. And that is the Yoneda Lemma. Or at least part of it. The remarkable thing about the Yoneda Lemma is that it's a proof at the level of categories, so it holds for any category of spaces, topological, metric, smooth manifolds, sheaves, algebraic varieties, anything. We begin the lemma by asking what information representables recover. Let C be a locally small category and fix A and C, inducing the covariant functor h sub A. For each covariant functor f from C to set, what are the natural transformations h sub A to f in the functor category C set? We should unwrap what this is saying in exact terms. Firstly, there is an isomorphism of sets, so there is a bijective function between the Hom set of the Hom functor at A and f of A. There are exactly as many natural transformations from h sub A to f as there are elements of f of A. Secondly, this isomorphism is said to be natural in A and f, suggesting that both sides are functorial in both A and f. Precisely, we can regard the left and right sides of this expression as bifunctors, from the product of the functor category of C and set crossed with C to set, and the Yoneda Lemma states that these functors are naturally isomorphic. In particular, the functor on the right is also known as the evaluation functor, since it takes a functor and an object as input and evaluates the functor at that object. I'm not going to cover the proof of naturality here, since there's a lot of algebra, but we'll just show the isomorphism for now. Let A to be a natural transformation from h sub A to f, and consider its naturality diagram. We'll trace the identity on A around the diagram. Along the upper path, we apply the component of A at A to the identity, then apply f of f to the whole thing. Along the lower path, we apply h sub A of f to the identity, which is, if you'll recall, postcomposition by f. So we compose the identity on A with f, which just gives f. Then we map it to the component of eta at B. But since eta is a natural transformation, these paths should be equal since the diagrammatic means. If we look at the function on the left, the input is always eta at A applied to the identity on A. This implies that any natural transformation from h sub A to f is completely determined by its value at the identity at A. This naturally induces a function mapping eta to the object that determines its value, and moreover, this function is a bijection, as every such value in f of A conversely extends to a unique natural transformation, and this establishes the required isomorphism sets. Naturality is left as an exercise. At the beginning of this section, we asked how much information we get when we examine how an object looks from all of the possible viewpoints. This corollary states that we recover the object up to isomorphism. That means that the maps into or the maps out of an object contain exactly as much information as the object itself with regards to the category. And I think that is a good place to stop.